So at the end of last class, we were basically doing what's called the Friedel-Crafts alkylation reaction. And oops. So aromatic ring, alkyl halide. So key point, it's an alkyl halide. So that means it is sp3 hybridized. This is and aluminum trichloride. This won't work with a vinyl halide or an aromatic halide. So both of these types of reagents don't work. It's just an alkyl halide. And so during last class, if we were looking to form this compound, this turned out to actually be the minor compound. And this one here was the major. And that was because the intermediate, which was a carbocation, undergoes a rearrangement to a more stable form. And this is the electrophile. So the way that this works is that you get a complexation between the halide and the aluminum trichloride to form a complex. This is basically just what we would have done in organic 1 if we're doing a Lewis acid base reaction. And then this breaks down to form the carbocation. And this would have a positive charge here. So with straight chained alkyl halide, there's a couple of limitations to this reaction. So the limitations basically are for straight chained, so linear, I guess, alkyl halides, you get rearrangements. Of the carbocation. So that's a pretty big. So this is for linear alkyl halides. You get rearrangements of the carbocation. So that's problematic. And we're going to see how the chemist overcame that in a second. For branched alkyl halides. I can't spell this morning. So something like this. Secondary or tertiary. This works well. So with linear alkyl halides, you get that carbocation rearrangement. With branched alkyl halides, it seems to work much better. The other sort of limitations, so this would be number 1. Number 2 was what we talked about last class, which was over-alkylation. So once you do the reaction aluminum trichloride. You form this compound, and I'll put this in brackets. And this is more reactive than the starting material. So this could go on to react preferentially again, for example. And that's because alkyl groups donate electron density. So they push electron density into the ring, and the ring is the nucleophile. So remember, nucleophiles want electron density. So the more electron density you have, the more reactive you're going to be. So the issue with overalkylation, we just assume that we deal with that the way we set up the reaction. So with the appropriate stoichiometry of reagents, using a large excess of starting material. So for this limitation, for what we're doing in the class, it's not really important because we're just going to assume that the reaction's done correctly, stoichiometry, like with the proportion of the reagents. But there are two other limitations to this reaction, and it actually feeds off of point number 2 here, the overalkylation point. This reaction fails with electron withdrawing substituents. So what are electron withdrawing substituents? Well, they're basically the same things that we talked about during the Diels-Alder reaction. So anything which will pull electron density off of the ring. So something like a nitrile, something like a aldehyde, or a ketone, or an ester. So this squiggly line here means this is where it's bonded to aromatic ring. There's a bunch of other groups, like even something like a protonated amine will also deactivate the ring. So I'll draw a resonance structure to show you what's sort of going on. So, and we would have done these resonance structures back in organic 1. So if we start with a ketone, we've got pi bond between electrons with different, atoms with different electronegativity. So we would draw one resonance structure like this. Negative, positive. Then we've got basically a positive charge, allylic to a double bond, so we could move those electrons there. And then we've got positive charge on the ring. And we can actually move this positive charge all around the ring. So that goes there. So we're going back to basically our fundamentals here. And then let's use green. This electron, these can go here. And I think you get the point that what we have here is a ring with positive charges in it, right? So all of these resonance structures, what they're showing us is that the ring is electron poor. So if the ring's electron poor, it loses, it becomes a weaker nucleophile. So in the case of strong electron withdrawing groups, like all of these ones that are drawn up here, this reaction just won't work. So you can't do a Friedel-Crafts acylation if you've got a ketone bonded to it. The reaction just fails. So that's, and it's all because the ketone is pulling electron density away from the ring, so it can't behave as a nucleophile. So that's the basically a third limitation. The fourth is interesting. Fourth, and that is if you've got an aromatic ring, and let's put this equals X. If X equals NH2 and R2 and HR, basically in a mean here, then the reaction fails as well. In this case, and it's for a completely different reason. It's because of the reaction that takes place between, say, we got NH2 and aluminum trichloride. What happens is the nitrogen just donates its lone pair to the aluminum, and you form a complex. Let's draw it like this. Negative, positive. And that becomes, so this, the protonated amine is very similar to this group here. And that's, this is, once this nitrogen gets protonated, it does two things. Number one, it kills the catalyst. So remember, you need the aluminum trichloride to be reacting with the alkyl chloride, not the nitrogen. So it kills the catalyst. And number two, then it starts pulling electron density inductively towards it. So ruins the reaction. So those are basically the four limitations. You can't have an amine bonded to the ring. You can't have strong electron withdrawing groups bonded to the ring. The second one here, overalkylation, we'll deal with that stoichiometry wise. And then the first one's just with the linear chained alkyl halides that you sometimes get rearrangements. So we're going to talk about how they overcome limitation number one, because it's a very similar reaction. But there is really no solution to number three or number four, unless, I guess in organic three, we talk about some ways that we could overcome certain things, certain strategies, but those are more synthetic things. The overcoming of problem number one is a very similar reaction, which is the Friedel-Crafts acylation. So instead of using an alkyl chloride, they use an acid chloride. And this will complex with the aluminum trichloride. Gonna get our lone pairs. So similar sort of thing happens. You form a complex. And then here something slightly different takes place. We are still going to make the so this will now have a negative charge. This will have a positive charge. And what I'm going to do is I'm going to boot that out like this. And this gives us and this could be in resonance with better keep it the same geometry here. The acyl cation. And so this is your electrophile. And the ring will attack it. All of the same restrictions apply, like you can't have an electron withdrawing group, that type of thing. But when this attacks here, you'll notice that there's only one, and I could have it attack either resonance structure here. What happens is that it can only attack one place. There is no rearrangement which takes place. And then we've got 1, 2, 3, 4. 1, 2, 3, 4. We end up making a ketone, essentially ketone. Now, and so this reaction always takes place at that carbon. So if we label this carbon as 1, 2, 3, 4, 1, 2, 3, 4, you always get there is no rearrangement. Now you might say, well, wait a second, this doesn't really look like 1, 2, 3, 4, this, because it's got a ketone there. Well, there's a neat little reaction that you can do that will convert this ketone into a straight chains alkane. So, and this reaction is, we will never do the mechanism of this because that would be painful. Zinc, mercury amalgam with some acid, and you heat this up. And this is the Clemenson reduction. And so this will reduce a ketone all the way down to the alkane. So it doesn't stop at the alcohol, it goes all the way to the very end. So basically, if you had a reaction and you wanted to, say you wanted to make this compound here, and you tried to use Cl with aluminum trichloride, and you made this instead, sad face. The way you could overcome this is to do the similar reaction, aluminum trichloride with the acid chloride to make and then do the zinc mercury amalgam, HCl, heat this up, and then you've got your product. So it's an extra step, but you made what you want to make. So it's one of those. The Friedel-Crafts reaction is we did like in the. I feel bad telling you what you missed out on, but you one of the reactions with hydrocarbons, we do a test for aromaticity using a Friedel-Crafts reaction with chloroform. So it's interesting. In that case, chloroform is this compound. And so this can actually undergo 3 Friedel-Crafts reactions sequentially. So if you did this reaction with aluminum trichloride and say benzene, then the first product you make is, so your carbon here, I'll star this blue. So that's this little carbon here. And now it's got, but it's got, now here it's got 2 chlorines on it, because one's been used to do the reaction. Then this reagent can undergo another Friedel-Crafts reaction with benzene. And this will make Cl. And then this can undergo a third with benzene, AlCl3. And you've made this compound which has got the 3 aromatic rings all sort of bonded together. And it's a neat little test. And during one of the stages, everything goes a really bright yellow. So it's easy to see. But anyway, that's, so most of the examples that are given in your textbooks and stuff, it's just got a single chlorine on it, but with certain things, you can actually do multiple on the same. So you're actually, this little carbon is undergoing this reaction multiple times. So that's kind of neat. So those are the main reactions of electrophilic aromatic substitution reactions. So just as a little review, if you have your ring, nitric acid, sulfuric acid, gives you a nitro group. We do bromine with iron tribromide, do the bromination. Similar with chlorine, although I don't know why you would want to use chlorine gas. Problematic. Chlorination. If you use sulfur trioxide and H2SO4, you make the sulfonate, or sorry, the sulfonic acid. This reaction's actually reversible. Like you can go backwards with this one as well. And it all depends upon the concentration of the sulfur trioxide and the sulfuric acid. So that's a reversible reaction. We won't talk about that much, but yeah, this reaction can be reversible based upon different conditions. What else did we do? So nitro group, bromine, chlorine, sulfuric, make a sulfonic acid. Let's make this a branched alkane alkylation. And the acylation. I guess there's one little point I should bring up as well. You will notice that there's no way to make this. There are a number of ways to actually take this nitro group and reduce it. Reduce. And this will make an amine. So common ways of introducing an NH2 group to an aromatic ring is to take a nitro group and then subsequently reduce it. The Clemmensen reduction does that. So it's a way of reducing an amine to a nitro group to an amine. So yeah, the Clemmensen will do this. Also, other things like we've seen this one before, tin dichloride under acidic conditions, and then you need a basic workup. And then iron and zinc, they both will reduce this with HCl to, and then this needs a basic workup as well. So what do I mean by basic workup? So if the reaction's got lots of acid in it, then your amine's going to get protonated once it forms. So you'll have NH3 and it plus, and you don't want that. So in your workup, you have a little bit of base, a little bit of hydroxide, and you will just deprotonate that to get your amine. So there's a number of different ways to reduce nitro groups to amines. Probably the one we'll use the most is this one, tin dichloride. But the Clemmensen also works too, because that's a zinc mercury amalgam, and if you use zinc and HCl, it reduces it, so the same reaction works. Okay, all of this is very interesting, but it gets even more interesting. And that's when you do these reactions when you've got different substituents on your ring, because that is far more interesting. Okay, so let's do some nomenclature. Just some really basic nomenclature of a ring. So if you've got an aromatic ring and you've got some group here, X, there's two different ways that historically people have named rings. This would be position 1, 2, 3, and 4. So sometimes you look at on a bottle of something and it might say 1,4-dimethylbenzene, for example. There's actually a common name for this, but anyway, what this would mean is that you've got a methyl group here and a methyl group here. There are also alternatives for each one of these positions. So position 2, is sometimes called ortho. Position 3 is sometimes called para. Oh, oops, nope. Meta. And that's where you find all your data. And then here is where this would be para. So the same So sometimes it might be para-dimethylbenzene, for example. So there's just different ways of naming it. For orthopara and meta are probably what we're going to use because it's easier. So right, so that's what we'll talk about. So I'm looking for some data here. So let's pretend that we've got an aromatic ring with a group here, position X. And then let's run a reaction here with HNO3, H2SO4. So we are going to do a nitration reaction. And so our product could be one of 3 different possible products. You could have your nitro group here. You could have your nitro group here. Or you could have your nitro group here. Where it goes, we're going to talk about that in a second, but there's another thing which is really important. And when I wrote X, I guess I should probably write Y. So what I'm going to say is that some groups activate the ring. And so when you activate the ring, you got putting more electron density on the ring. So this would mean that the reaction is faster. And some groups are going to deactivate the ring. And so this is going to be slower. And so we have already seen an example of this when we talked about the Friedel-Crafts alkylation or acylation reaction. If you've got a strong electron withdrawing group, the reaction fails because the reaction is so slow, it becomes useless. So for example here, in this reaction I've done above, I'll put X equals whatever, and then the rate. So the rate. So when X equals nitro, so remember, nitro group is a strong deactivating group. The reaction rate is 6 times 10 to the minus 8. Pretty slow. If it's just hydrogen, which would be benzene, oops, no. We'll move hydrogen over here. Hydrogen, which is benzene, that rate is basically given the rate of 1. So everything's compared to that. If you have a chlorine group, so remember, chlorine is an electronegative atom. So it's going to pull electron density out of the ring just because it's chlorine, because of its electronegativity. The rate here is 0.033. So NO2 deactivates the ring through resonance. Chlorine deactivates the ring through induction. And if you have OH, so OH is electronegative as well, but it donates electron density through resonance. So the rate of a hydroxyl group is basically 1,000. So this is really, really fast. So an OH group will activate a ring. So we're going to draw some resonance structures to basically show this. Okay. So Now, the other part is that, okay, so both of these groups here, because everything's compared to hydrogen, right? So this would be an activator. Reaction rate's faster. Both of these would be deactivators. So slow. Slow, fast. Now, there's basically, we haven't talked about the types of products that would form here. So this one here is an ortho. This one here is meta. And this one here is para. There's basically 3 different types of groups that we can put on the ring here. I've broadly classified these so far as deactivators and activators, but there's technically 3, and we're going to see how this works in a second. So activators, so 3 classifications. First one is activator. Activators direct ortho and para. So if you have, say, a hydroxyl group, and you do this reaction, your 2 main products are going to be the ortho and para. Now, which one's the major product? For what we're going to worry about in this class, some people would say, well, the ortho looks like there'd be more sterics there, so it should be para. Sterics, when you do a big bulky groups, para is the predominant one. But for what we're dealing with, what I'll do on a test is that I will say only draw the ortho isomer or only draw the para if there's an option. And then that gets me to be able to test you if you know what para and ortho is, right? So, and it's hard to know without doing the experiment. So I would never, so for what we're worried about, I'll say just draw the ortho or just draw the para for whichever question. So that is, so with the hydroxyl group, these would be the 2 major products. The meta product would be minor, like 2% or something like this. So activators, it's nice because it's always the ortho and para. And I'm going to be able to, I'll show you how you'll always get this right. You'll be able to always know where it's going. So that's the first class. That's number one. There are basically 2 types of deactivators. There are deactivators that direct ortho and para. And then there's deactivators that direct meta. And so the nice little bit about this is that the chlorine is so the chlorine is ortho-para director, and the nitro is a meta deactivator. And so I'll show you how you can always get this right. So there's yeah, let's do that. And it all comes down to and so we'll be able to bundle, I'll be able to show a group and we'll be able to bundle it into one of these three categories. Okay, so how do we know? Oh, it sounds like a Whitney Houston song is about to start in my brain here. How do we know? Okay, so the trick we're going to use is basically resonance structures. Let's do chlorine first. Okay, so an example for the chlorine. Chlorine. So what we'll do here is chlorine's got a lone pair, and it's in the benzylic position compared to a double bond. So we can move that lone pair here and then move that there. And this is going to give us this resonance structure. Then we can move this lone pair here. And this will give us this resonance structure. Oh, we're not done yet. Let's do one more. Let's move that there, and then this bond here. And then finally, we can go back to where we started. We can move this there, that move. Oh, I guess I forgot my positive charges here. Plus, plus. So what you notice immediately is that where are the negative charges? Let's ask this question. Where are? Well, in this case over here, it's ortho. Over here, it's para. Over here, it's ortho. And what type of director is chlorine? Or the halogens, I should say. Because I could have put a iodine there. I could have put a bromine there. These are ortho para directors. So if you do a resonance structure with those benzylic lone pairs on the halogen, if it's chlorine or bromine or iodine, the negative charge in the ring is where the substituents end up, ortho or para. And so remember, for these reactions, the ring is the nucleophile, And look, we've got negative charges, which would do the attacking ortho and para. So it's beautiful. So you always have a negative charge where the ring attacks from. So and the same thing, this would be, you could draw a very similar resonance structure for our friend here. Oh yes. You could draw resonance structures for like a hydroxyl group or whatever. It'll be exactly the same, like negative charges. Will be ortho and para. And it turns out that's exactly where the products are. So that is the one beautiful little bit for this, is so that we could look at a substituent and see, oh, does it have some lone pairs there? Draw some resonance structures, boom, it's going to be an ortho-para director. So that's this is one beautiful example. Let's do the nitro one now. All right, and so our nitro group looks like this. So the nitro group, remember, this is one of the weird functional groups that's got a built-in, which has got built-in formal charge, because we can't depict it accurately because it's really a nitrogen 1.5 bonded to oxygen. But if we look at the nitro group, immediately when we go back to our pattern recognition sort of thing, is that you'll see that you've got a positive charge beside a double bond. So that means you can move that double bond to make a bond there. But nitrogen's already got 4 electrons, so we'll need to move those electrons onto the more electronegative oxygen atom. And this gives us the following. So we've got a positive charge in the ortho position. Let's draw another resonance structure. Okay, so we can stabilize this charge by drawing another resonance structure. And here we go. Negative, negative, plus, plus. Okay, positive charge is now para. And let's draw another resonance structure. Let's move that there. There we go. And then I guess we could go back to where we started by doing this. These electrons go there, goes there. Okay, now we're going to ask ourselves, so the ring behaves as a nucleophile, right? So the ring so keep that in mind. The ring is a nucleophile. So on the ring, where is the electron density? So where's the electron density in the ring? There is no negative charge in the ring, right? It's been sucked out of the ring by the nitro group. So, and in the ortho position and in the para position, we've got positive charges. So the only location where there isn't a positive charge is meta, the meta position. Because ortho and para have positive charges. So with the nitro group, it is going to direct meta, because that's basically where the only position where there's not a that's where the only position where there's some electron density. We could actually do some, if we do the mechanism, we could look at some transition state structures, and we'll see that if you draw similar resonance structures once you've started your the actual reaction, there'd be some destabilizing or stabilizing drawings we could do. So, right, so that's basically the three different types and why groups go where they go. So the reactivity and orientation is basically based on inductive effects and two resonance effects. So with regard to the, say, when we had this chlorine group, so the chlorine is pulling electron density away. So inductively, it's deactivating the ring. But through resonance, with resonance, it's directing ortho and para. So there's, and in some groups, they withdraw electron density through resonance and inductively. So like the nitro group or the cyano group, if you think about the nitro group. Positive. You got a positive charge there, so the electron density is being sucked towards the positive charge. So this is inductively, it's removing electron density. And through resonance, we've already done this whole bit up here. Through resonance, it's removing electron density. So some, like the strong deactivators, inductively remove electron density, and through resonance, remove electron density. The halogens are the group which inductively deactivates the ring, but through resonance directs ortho and para. And then groups like the hydroxyl group or an amine would activate the ring through resonance strongly. So that's one of the groups which textbooks never talk about, which is interesting, is fluorine. Because what we've learned in class is that fluorine is the most electronegative atom, and it should be pulling electron density like crazy out of the ring inductively. But it turns out fluorine is actually an activator. And so you don't see this in any of your textbooks because it breaks this rule. So if you want to know the answer to why fluorine activates rings for electrophilic aromatic substitution reactions, you should take Dr. Yan's class on group theory, because I think they talk about that there. Anyway, the other thing to remember is that alkyl groups donate electron density through induction. So that if you've got a methyl group, this will be an activator. And so therefore it's going to direct ortho and para. So, and you can think about this in the sense that if we were to draw out our aromatic ring and put on a methyl group, let's draw our ring, put our beautiful p orbitals there. Look at that, nice, lovely. And then let's put on a proton. And this electron density in this bond gets donated through space into the pi system. This effect is called what? And the bond has to be lined up so it's exactly eclipsing that sort of. So if this is your p orbital, this proton has to be right there so it lines up perfectly. Not because the hydrogen doesn't move, it's just donating its electron density. It's a type of conjugation. How about that? If this was a carbocation, you would be using these electrons to stabilize this positive charge through this effect. Right, hyperconjugation, right. So alkyl groups basically donate electron density through hyperconjugation. So they will be activators and they will direct orthopara. So we can go through and look at a whole bunch of different functional groups and sort of classify them as orthopara or meta directors. So, and the trick will be, so let's do that here. So this little squiggly line is going to be our aromatic ring. So the way I would view this is that just think of the resonance structures that these groups have. So if you've got a ketone, for example, we can draw a resonance structure where we move these electron density onto the more electronegative oxygen. And actually, let's draw the ring here just for a second. And if you've got a positive charge beside this ring, this is what's there's gonna be a resonance structure where you move that over. So you're gonna move that positive charge into the ring. If you've got, and so similar sort of situation way over here. So if we move the pi electrons onto the more electronegative group, then we've got this issue where now we can pull electron density out of the ring to go to that positive charge on carbon. So both of these will therefore be deactivators. And because you have a positive charge in the ring, and if you draw all the resonance structures for these, you'll see that the positive charge is always ortho or para. This means that they're going to be deactivators and they're going to be meta. It's going to go meta. Meta. So any group which, when you draw a resonance structure, has a positive charge on that carbon right beside the ring, those are all going to be deactivators and they're all going to direct meta. Now, conversely, if your group has got some lone pairs that it can donate into the ring, like an oxygen or iodide, these are going to be ortho para directors. Ortho directors. Because if we were to draw this resonance structure here, this OMe, oxygen's going to have a positive charge, but you've got a negative charge on the ring in the ortho position. And then we could draw another resonance structure where it's in the para position. Same thing over here. The iodide would positive, negative. So we can just, but this basically goes all the way back to drawing resonance structures. So this will be the little, this will be the little sort of, you got to just remember that. So, let's do an example. We had BR2, FeBr3. Because we've got an oxygen which can donate electron density into the ring, this will be an ortho para director. And so our products should be E. See, it takes a lot of time to draw two things. So we'd probably only say draw one of them. What's another example? Let's do something we haven't seen and get everyone to. So if we had, say, No, let's do something different. Let's do okay, think about these two reactions for a couple of seconds, and then we'll, or try to do them, and then we will do the answers for them. So the actual reaction rate, we don't care about that. But what we care about is the substitution pattern. Is the group on the ring going to direct meta, or will it direct ortho and para? Okay, let's go over these here. So the first reaction is a nitration. The second reaction is a Friedel-Crafts acylation reaction. Okay, so with the ester attached this way, what there is basically a resonance structure. I'll draw it over here to the side. Where we can pull electron density out of the ring, and it's got a positive charge, and this positive charge will be a resonance structure where it goes positive charges here or here or here. So the first one does direct meta, which a couple of people have messaged me about. So our product will look like this. So this ester directs meta. Now, it's funny, the second reaction is also an ester, right? But we've changed the connectivity of how it's bonded to the ring. So in the bottom example, and we'll use purple, here the lone pairs can donate electron density into the ring. So we will have a negative charge in the ortho position. And remember, it's a negative charge which is attacking, so this will direct ortho and para. Well, resonance structures would be there. So this product, and I'll only draw the, we would get two things. Let's draw the para because it's going to be easier to fit on the page. It would look like this. Oh, 1, 2, 3, 4, 1, 2, 3, 4. So that's, and then plus the ortho version. Right, okay, so that's basically, so at the start of next class, we'll do a bunch of little examples of this sort of thing. That's basically the electrophilic aromatic substitution. When you got a substituent, yeah, so we'll go over this a little bit more on Tuesday. So someone asked, can we discuss the plan for next week? And like, will Thursday's class be a review, or will Thursday's class be a class? I don't know yet, to be perfectly honest. There's one more little section that I think we absolutely need to cover. Someone asked a few weeks ago, I hear that we're really far behind. Dr. Fan said we're super far behind. And I said, oh, no, we're not. The truth was that, yeah, we kind of are. So so there's no hope that we could get through everything which was on the Organic 2 syllabus. So we'll just find a good place to stop. And that might be at the end of Tuesday's class, and Thursday would be a review, or we might have to go halfway into Thursday, but we'll see how it goes. I'd like to do 2 little mini assignments, one on the aromatic stuff, which I'll try to get that out today or tomorrow, and then another one on this sort of stuff, just to roll, so you've got some practice stuff for the final exam. Our final isn't until like the 23rd or something crazy like this, really far into the exam. I think it's the 23rd, I might be wrong. Might be the 17th. But yeah, it is the 23rd, okay. But whenever it is, we'll set up some tutorial classes before the final anyway, so like during the exam period. So we'll set all that up next week. All right. I think that I've posted lecture notes for the electrophilic aromatic substitution reactions. So if some of the stuff I said today was a bit didn't make sense, there's more detailed notes on Moodle for this. I tried to hit the highlights. The key part is that if you've got some functional group on the ring, we should be able to, if we can draw resonance structures of it, determine if it directs ortho or para based upon those resonance structures. So that's the real take-home message I wanted everyone to learn. And if it does, if your resonance structure pulls electron density out of the ring, so you got a positive charge, for sure it's going to be a real strong deactivator like nitro, like the nitro group. Anyway, I'll check everybody's answers to the practice questions, and I think I noticed that some people were forgetting about the rearrangement, which was a side effect of the Friedel-Crafts alkylation reaction. So with linear ones, you do get those hydride shifts and stuff. So just keep that in mind. So if you've got a long chain, it's better to do the acylation and then the reduction, the Clemenson. All right, so if you have any questions, just fire me off an email and I'll see everybody on Tuesday, but I'll probably send you an email before Tuesday. But have a good weekend. I hope everybody is, term's almost over. I hope you're having, I hope there's a good light at the end of the tunnel, so to speak. Yes, you too. And I'll try to get this lecture up as soon as possible.